Higher order derivative sounds a lot more complicated than it really is. It just really means that we're taking the derivative of a function more than once. All right. The notation could be a little funky though. All right. So if you take a derivative a second time, we call that a second derivative. That's not the part that's funky. It's just when you look at something like this, for example, it might be a little intimidating. All right. But if we kind of keep it simple, we look at something basic like f prime of x. Right? We know that when we have a function of x and we take its derivative, we call that f prime of x. So if you want to take the second derivative of that function, just throw on another prime. All right? So f double prime of x. All right? Then f triple prime. But after a while, indicating the number of primes can be a little challenging if you're going with little tick marks. So we go with more of an exponential looking sort of thing. It's not really an exponent. That's why we put it in parentheses. But if I want the fourth derivative or beyond, I would just put whatever level of the derivative that I'm looking for, I put that in parentheses. So if I need the 19th derivative, then I would do f as a power or superscript really of 19, right, in parentheses. All right. But this other notation here can also be kind of funky. So when we say d over dx, what we're saying is the derivative of some function, some unknown function with respect to x per unit of change in x. All right. So when we would say something like dy over dx, what we're saying in this instance, oops, that's a little thick. Gonna get a little overzealous there. We're saying that y is a function of x. So this would be the same as dy over dx, which we should be pretty familiar with. We've seen that a lot. All right, so dy over dx. So if y is equal to f of x, this would be d dx of y, or d dx times y if you want. If you multiply a d by a y, it just becomes dy. All right. So that's the connection between this notation and this notation. All right, they both essentially mean the same thing. All right. Now, if I want the second derivative, that second derivative would be noted this way, where we have d with a power of 2, dx squared. All right. So that's saying the second derivative of some function of x. The original function hasn't changed. It's still some function of x, which we typically denote as y. All right. So that would make this the same as d2y over dx squared. All right. So notation-wise, that's where things get a little dicey, because in the past, anyway, maybe I'm doing a wonderful job of explaining this and it won't come up again, but it almost always does. Why the 2 comes after the d on the top, but it doesn't come after the d on the bottom, it comes after the x. Like, why is that the case? It's because the original function isn't being squared, right? It's still the original function. It's still the second derivative of the original function. The d is representing a change, right? So that's talking about the second aspect of change in y, or the change of the change in y per unit of change in x squared. Right? That's why you have some, like when we're talking about acceleration, we say meters per second squared. Right? It's still meters on the top, because the function of x, the position function of x, is measured in meters. That didn't change. It's just what aspect are we looking for in terms of the horizontal relationship. Right? We're looking for the squared change. In that case, it would be time. All right. So it's a little weird, but it's consistent, and consistency is a good thing because you can always kind of rely on consistency until the theoretical part starts to make more sense. All right. You'll see that when we get into some concepts down the line where it'll be like, all right, I'm just going to follow the steps until I understand what the heck is going on. But for now, at least I have steps to follow. It doesn't always play out that way, but for this kind of stuff, it will. All right. So with that in mind, something like d as a power, or with the power of 3, dx cubed, it will make more sense that that's going to be the third derivative of the original function f of x, right, per unit of change in x, per unit of change in x, per unit of change in x. All right, that's why when we say things like meters per second squared, we're saying meters per second, right? That's the rate of change. Right? How fast is the velocity changing? The velocity is meters per second. How fast is that changing every second? When you talk about the element of jerk, right? So you're talking about position, velocity, acceleration, and then jerk would be the third derivative. That's the rate of change of acceleration every second. So that's meters per second squared per second, right? So there's an intuitive way of understanding this, but the notation can somehow, or sometimes, I guess, make it seem less intuitive. All right. So you see other forms of notation here. I would say for our purposes, the least important one would be this. We won't be using this, at least not in this class, but I always include it because I don't know where you're going to end up after this. All right, you may need it. All right, but y prime, y double prime, y triple prime, and all that, that works the same way as the f primes, f double prime, and so on. Desmos will handle second derivatives just the same way it handles first derivatives. The problem is it doesn't give you the equation, it just gives you the graph. So if I say f of x is equal to x squared. Now we know that the derivative of that, or we should know, the derivative of that is 2x. So if I put in f prime, I get a graph that looks very much like 2x. All right. Now if I want the second derivative, full disclosure, for the longest time I didn't know that this would actually work because I thought you needed to use like quotes, but you just use prime a second time. So a second, oop, that's not a prime. There we are. It doesn't create a graph because it's a constant, but the derivative of the derivative, so x squared has a derivative of 2x, derivative of 2x would just be the constant 2. It doesn't even bother with the graph because it's reporting a constant value, right? Although I would think it would be kind of nice to have it as a graph. If you want it as a graph, you just type in y equals. I feel like that's kind of a step that shouldn't be necessary, but it is, right? Because technically, I don't know how aware you are of these little things, but if you type in y equals f of x, I'm sorry, y equals x squared on Desmos, or if you just type in x squared on Desmos, it'll graph it just the same either way, right? It graphs expressions just like it graphs equations. I think that's incorrect. It definitely is incorrect, but it does it anyway. All right. So when you put in the derivative function, it really should be y equals f prime of x. But Desmos kind of lets you get away with that, right? It just kind of falls apart when there's a constant value as a result, right? It won't give you the graph, it'll just give you the number. But it's constant, so who cares, right? So if you know it's always going to be 2, then you're like, okay, well, the second derivative is always 2, and that's all I needed anyway, right? And if you needed to come up with the graph, you say, okay, well, what does y equals 2 look like? It looks like a horizontal line, so you're good to go there anyway. Powers of n just means the nth derivative, all right? We're not talking about infinity here, right? We're just saying some unknown large level of the derivative. So like the 99th derivative or something like that. Right. In terms of computing the derivative, well, the level of difficulty is strictly dependent on how complicated your original function is. So my f of x here, let me make that a little bolder. 12x to the 1/3, right? Just rewriting it to get it into the power form. So if I want to take the first derivative of this, I would just apply the power rule. Multiply power by coefficient, reduce the power by 1. All right. So power by coefficient, 1/3 times 12 is going to be 4. reduce my power by 1. 1/3 minus 1 is negative 2/3. So for my second derivative, just do it again. All right, so that's not too bad. You just multiplying and subtracting a second time. So negative 8/3 x to the negative 5/3. All right, so that would be my second derivative. You always want to use the same notation that the question presents you with. All right, they use f of x. We don't want to go dy dx for our derivative. We go f prime of x. All right, you could also use d dx of f of x. That's fine too. All right, but you don't want to switch over to y's without establishing that first. All right. We need the second derivative of h of t. So we'd find the first derivative of h of t. As long as you know the derivative of sine and cosine, it's pretty straightforward. All right, we just hang on to the constant multiple. So that 4 comes along for the ride. That negative 5 comes along for the ride. The derivative of sine. What is the derivative of sine? Cosine. Bless you. And the derivative of cosine? Negative sine. All right. So then simplify a little bit. Now, under normal circumstances, I wouldn't ask you to do that. But since we have to take the derivative again, we want to have it in as compact form as possible. So that makes life a little easier. All right. So 4 cosine t, this would be plus 5 sine t. Again, that's h prime of t. All I did was simplify it. I haven't done anything else to it yet. To find my second derivative, I'm bringing the constant multipliers along for the ride. Then I'm taking the derivative of each part. So derivative of cosine again. Negative sine. Same negative sign as before. Derivative of sine. Cosine. Yeah, so we're not inventing anything. When nobody's asking for the limit definition of a derivative anymore, this is just fact-based knowledge. All right? You know the derivative of sine is cosine. Derivative of cosine is negative sine. Hopefully you know the derivative of tangent is secant squared. If not, add it to your list of things to know. Right? You can reference your notes when you're taking an assessment, but it makes life so much easier if you know those basic facts. All right. Now at this point, because I'm not asked to do anything additionally with this, I would just stop. Yeah, I mean, I could simplify a little bit, but it's not necessary. All right, so I would just leave it at this. All right. Now the next one, and last one that we'll do together for today, find the 99th derivative. All right, so there's a reason why it's the last one, because it's going to take the rest of the period to do. All right, it is what it is. So we have k of x. We know that that's equal to the sine of x. K prime of x. Derivative of sine again is what? Cosine. K double prime, taking the derivative of cosine, which would be negative sine. Yeah, we're just going to go back and forth here like 99 times. All right, so here we have a negative sign, but we kind of look at it the same way we looked at these problems before. We have a constant multiplier that comes along for the ride. In this case, I could just write it as a negative sign, like negative SIGN sign. And then put in the parentheses the derivative of sine, which is again cosine. All right, so now we could write the simplified forms here if we want, but there's not really much to simplify. It's just removing parentheses. The fourth derivative. Again, we bring the negative along for the ride. Derivative of cosine is? Negative sine. Oh, that moved out on me. Now that's the same as saying sine of x. Yeah, we get a nice cycle here. So if you remember powers of I, it's the same idea there. It's a mod 4 cycle. All right, so we really don't have to do this 99 times. Although when I have had classes in the past that didn't recognize that it was a cycle, I would just keep going.
Did you just like actually go through 99?
Yeah, it took 2 class periods. Yeah. Because the hope was that they would recognize that there was a pattern, and since they didn't, I wasn't just going to give it to them. So we just kept going. Never recognized it. So I'm like, all right, I could do this. I'm getting good at it. Yeah. I'll tell you right now, at the end of that process, they all knew that the derivative of sine is cosine, and the derivative of cosine was negative sine. So, so anyway, we have our first derivative, second, third, fourth. It's kind of like a more insane version of when we did that thing with the powers, when I was showing you about logarithms. Like, oh, what if we change it? What if we change this decimal a little bit until we got there? Any oscillating functions where one becomes the other through the differentiation process.
For like the notation of the first 3 derivatives, is it always using like the tallies, or can it be 1, 2?
As long as the 1, 2, 3 are in parentheses, you're fine.
Oh,
Yeah, just don't write it as a regular power. So any multiple of 4 would get you back to a sine function. If I go, I mean, I could count by 4s if I want. Or we could just jump to 96. Or jump to 90, or jump to 100 and dial back 1. So a multiple of 4 that's closest to 99, 96 or 100 if you want to be on the low side or the high side, it doesn't make a difference. But if we cycle back and forth over and over, eventually we would get to the 100th, and we could work our way back, 99th, 98th, 97th, that's not a 9, 97th, 96th, 95th, and then it was blah, blah, blah. All right, all because it's multiples of 4. So the 99th derivative would be negative cosine of x. So notation-wise, I would say k superscript in parentheses of x would be equal to negative cosine of x. Yeah, but if you had something like just an ordinary power function, eventually it would get to 0. Like when I talked about x squared before, x squared has a derivative of 2x. 2x has a derivative of 2. 2 has a derivative of 0. 0 has a derivative of 0. 0 has a derivative of 0. It's never going to move off of 0, no matter how many more derivatives you take. So that wouldn't kind of relate to this concept. In fact, actually, I mean, I could make a problem out of that, but it'd be more like a trick question rather than anything that kind of moves the plot along. Right? Because the 99th derivative of that function would just be 0. Right? Because the rate of change wouldn't change anymore. All right? But any type of function, like we were saying, that oscillates back and forth from one function to another through the differentiation process would tie into this idea. All right. You could also do it with exponential functions like exponential e, because e to the x has a derivative of e to the x. Actually, that's a good example. I'll also take it as a typo.
So would it just be e to the x every single time?
It would be, unless I jazz it up a little bit by saying find, I'll keep it a little simpler, the 10th derivative of f of x equals e to the 2x. All right, yeah, because if it was e to the x, then every derivative would be e to the x, whether it was the first or the 4,000th. All right, but when it comes to this, the first derivative would be e to the 2x times 2. All right. When you find the derivative of exponential e, you rewrite the exponential, and then you multiply by the derivative of the exponent. All right, so that's where that 2 is coming from if you forgot. Over a holiday break, I probably would have forgotten. So then that 2 serves as a constant multiplier. So my second derivative, or in my second derivative, that 2 would just come along for the ride. And again, I would take the derivative of what's inside the parentheses, which we've actually already figured out was e to the 2x times 2, which amounted to 2 times e to the 2x. Which would become 4e to the 2x. All right. And if you don't figure out the pattern, because there's always a pattern with these types of questions, that's the whole idea. It's like, I mean, there's a very rare type of evil math teacher that would give you a problem that involved the 10th derivative in which there was no shortcut, no pattern to it. All right. So if there's ever a situation like this, there's always a pattern. All right. So we're looking at this, and maybe you see the pattern, maybe you don't. If you don't, do it another time. Find the third derivative manually. Drag down that 4. The derivative of e to the 2x, it's still 2e to the 2x. If you don't see the pattern, then if you never see the pattern, you may have to do it 10 times, but hopefully not, because here we're looking at powers of 2 as a coefficient depending on the derivative. All right. So if we write this using powers of 2, I could look at this as 2 to the first e to the 2x, 2 to the second e to the 2x, 2 to the third e to the 2x. So everything remains the same here with the exception of the power of 2. And that power of 2 seems to be consistent with the level of the derivative. So when they ask me to determine the 10th derivative, it's going to be 2 to the 10th e to the 2x. Just by making that pattern recognition. All right. A little spicier. Actually, maybe easier. I don't know. It all depends. It depends on what derivatives you know. Right? Because if you're constantly having to go back and forth to a reference guide to refresh your memory on derivatives, then it becomes more challenging. Still very doable, but more challenging. Right? But if you have some instant recall on some of the basic derivatives, you know, like if you know the natural log of x has a derivative of 1 over x. If you know e to the x has a derivative of e to the x. Sine, we talked about that. Cosine, same deal. All right. The basic stuff, then you're in pretty good shape moving forward. All right. So, oops, I don't know what